Hey guys, for the patience.
It's not, yeah. It's like kind of by hand. It's by hand. So it's easier than what you're doing hard.
Today we have the third and last of Lady Jerison Zygmund Calderón lectures on development sets of solutions to semilinear elliptic pieces.
Okay. Thank you again, Carlos. As I've said before, it's a great pleasure to be here and an honor to address you. So, as Andre suggested, we'll start with a 2D case and just remind you what we did last time. Especially, I don't know whether that tape from last time is going to be there.
I think the audio
Schmool's iPhone.
we have the audio.
The audio. Well, you know. Okay, so the situation is the idea is the following. We want to get as close as you can't get entire functions, which have all of whose level sets are quadrics, but you can get almost there with this sort of exceptional slit. And in 2D, the example you can do it with all the quadrics. And we're considering the entire family of quadrics. So the way that you do it is using a conformal mapping. So here are the complex coordinates of Euclidean space. And then you write down cosine theta plus it. All right? So that's the mapping. And this maps, this gives you a corresponding coordinate system. Now, this isn't quite the coordinate system we're going to use, but first I'm going to draw a picture of it. So, recall that if you take the level sets t is equal to a constant, they're going to be ellipses. You can see that. It's easy to see that. Now, the way that this works. So I'm just reviewing now what we did last time. There's a slit. If you take the constant t equals 0, you're going to get a slit, a needle, if you like. Wow, this thing's a little rattling. Okay, so you get a needle because of course this just goes from -1 to +1. All right, and you should imagine it as a collapsed ellipse. If you had one which was really close to it, it would circle around. So it really traces it out twice, as you can see when you go from theta equals -pi to pi, it traces around the sort of, if you like, the top of the segment and the bottom of the segment. All right? So that's the situation here. And it turns out that all of these ellipses are confocal. That is, the foci are at ±1. So this is what I said last time. And those are the level sets. And that function is literally the function t. It's the coordinate t. That's all that's happening.
So the harmonic function of Riemann is just
the harmonic function is t, all right? Or of course a constant times t would also have the same level sets, okay? So that's the harmonic function. And then there's another harmonic function which has the name theta. And that's, when the theta is constant, you're getting hyperbolas which are also confocal. And you can map this all out. Now the interesting thing is that if you also take theta, some constant times theta plus some other constant times t is equal to a third constant, then you're getting these things which are analogous to Bernoulli spirals. All right? The hyperbolas and the ellipses meet at right angles. They're an orthogonal coordinate system. And these other things are spinning around. And so I drew last time the case of polar coordinates where you collapse the foci to the middle, and so you can see what those would be, easily imagine them. That would be the case log r. C1 log r plus C2 theta is equal to C3. Those are called Bernoulli spirals. Okay? Okay? So those are the other trajectories that we're interested in. In higher dimensions, we have confocal ellipsoids and we have confocal hyperboloids.
So when t equals 0, then it's just that needle, and then either t positive or negative, you get like this neighborhood of the needle.
Yes. Now, so this is the picture. But when we do computations with this and we translate this into a question in algebraic geometry, in disguise, what we're going to do something on some kind of Riemann surface, and the Riemann surface in this case is a cylinder. All right, it's S1 across the real line. In 3 dimensions, it's the Riemann surface is a torus. It's S1 cross S1. And in higher dimensions, the genus is the least integer in half the dimension. Which maybe I'll say a little bit more about that. But anyway, the way to make the translation requires that you think about the variables. I'm going to give them new names, U1 and U2, so that there's proper symmetry between them. And then the interesting object of study when I transplant to these new, so I'm going to look at everything in U1, U2 coordinates. And then what happens, and what happened last time, is that we realize that these should be complex numbers. All right? So we've completely destroyed our intuition about what this is, but all we're interested in is formulas. So it doesn't matter. Okay? So we have the standard metric on Euclidean space, and now we're just going to write it in the U1, U2 coordinates. And lo and behold, when you do that, it's sine U1 plus U2 times sine U1 minus U2 times du1 squared plus, so maybe I'll just du1 squared minus du2 squared. Okay? So what we've gained by this is an important symmetry, which is that if you exchange U1 and U2, you get the same metric. All right? And that turns out to be just incredibly important to the algebra, and in higher dimensions it's even more important. Okay, but it's already essential here. All right? Now it just so happens that there's another way by a trigonometric identity of writing this, and both of these presentations are relevant in all dimensions. The other way of writing it is sine squared U1 minus sine squared U2 is the factor on du1 squared minus du2 squared. So this is the situation. Now, what's the goal? The goal is the following. We start with an arbitrary, so here's the goal. Given U, which is harmonic, and whose gradient does not vanish. And I'm going to cheat. Actually, its principal curvatures, also of its level sets, can't vanish. All right? So I won't say that, but that's what's going to happen here. Find a formula, a magic formula, for a metric G tilde, which has indices ij, and you can do them in any, so this is just a 2x2 matrix in this case, all right, which has a formula which is some algebraic function of grad u, grad squared u, and grad cubed u. So it's some polynomial over some other polynomial, all right? And the degree is pretty high, and it depends on on third derivatives. It's kind of a messy object. So by the end of this lecture, I will have written down for you exactly what this formula is. All right, but I have to tell you some stories about it, how I thought it up, okay, and various other things. So find it such that if you did it for if U is equal to C1 U1 plus C2 U2, this model, the solid time, then this guy turns out to be equal to du1 squared plus du2 squared. So what this is doing is it's saying this is analogous to exponential coordinates and the idea of a Riemannian manifold, which is that we have this model thing, which is just sort of the perfect guy, and everything, we're getting sort of the best approximation to it. We're oscillating by this thing, which is a quadratic or something like that. And in order to do that, we need the cubic terms. All right? So that's what we're doing. All right? And we want to do exactly the same thing in all dimensions. And I'm honest to God, even though I shouldn't be saying this, I am very close to getting there. But as I warned you last time, if you do it by stupid methods, you get a massive, ridiculous thing which can't even be done on a machine. It doesn't even finish the formula. You can't even simplify the formulas. They're so huge. But I do believe that so, and I'll be able to explain to you not only the two-dimensional formula, but what the extra piece is in higher dimensions and why it is that it's a little tricky to figure out what it is. Basically, what happens is that it's easy to figure out what's going on the quadrics themselves. So that's the case where you just have a multiple of one of the two coordinates or one of the n coordinates. Then you could do it, but it's already complicated in that case. And the amount of linear algebra involved makes it hard to guess what's going on when you tilt it, when you take combinations. But the reason why the combination should work is exactly trigonometric identities. It's the fact that there's a sum formula for the sine function, and there's exactly the same type of thing. This is exactly the point of abelian integrals, which the word abelian for addition comes from these kinds of integrals. This is historically where the word comes from. And Abel discovered that there was this abelian property of these integrals, and then Jacobi actually solved them in this context of these expressions. So these ones come from elementary integrals, where we have one d mu over mu minus a1 times mu minus a2, right? Square root, right? So you know that those come out to be trig functions. Those are the functions. Well, if you have 3 factors, this is an elliptic integral. If you have 4 factors, it's still an elliptic integral. But if you have 5, it's what's called a hyperelliptic integral. And it goes on from there, and there's algebraic geometry associated with these things. Okay? So you get a hyperelliptic curve, which is a curve of higher genus. All right. Okay, so that's the frame of reference, and maybe I'll remind you also that in 3D, the relevant formula I'm claiming, the one you have to worry about is one or the other of these two formulas. All right, this is our model that we're going to have to try to work with. All right, but we're going to do everything invariantly. All right. In 3D, the standard, the object here, which I wrote down last time also, which I think, given that there was no camera, this is probably not a bad idea to write this down again, is P1 minus P2, P1 minus P3, du1 squared plus symmetric. In these things, where the PJs are functions of UJs, j equals 1, 2, 3, and these are the Weierstrass P functions. It's just one Weierstrass P function, the same one for all the coordinates, which is incredibly important. This is the fact that this is symmetric is part of it. Is one of the main points. Now, there's another presentation. So that one is analogous to this, all right? And in fact, when Jacobi originally wrote this down, he didn't write them down in terms of P functions. That was invented 30 years later. But in fact, they're reciprocals of a Jacobi function, which is called the Sn function, Sn, which is exactly supposed to mimic the sine function. So it's very parallel. So this other presentation is the one that's expressed in terms of Jacobi functions. I'm not going to write it down because I'm never going to get even to the
And in that case, what would be U1, U2, and U3? how would you find U2 and U3? Or what is the substitution you have in mind there?
Yeah, oh, I'm sorry. Let me say what P is. So P of mu is the integral d mu of the square root of the product of the mu aj's. This is the pattern in general, okay? And you have the upper half plane. You have A1, A2, A3. This works in general here. And if you confine U1 to this, so let me write down one more object, which I did last time, but I should fill this in. There's no point in not doing it. So remember, I wrote this down here. Okay, and now there's a convention that the sum of these guys is equal to 0, which is just a translation. So these things are the equations for all the quadrics, and depending on where mu is, mu1 is between minus infinity and a1, and the next one is here, and so on. And now what you do is you solve this integral equation, which is this denominator is literally just the product of the denominators of this thing here, and of course its degree depends on the degree of the dimension. Okay.
Understand.
And now you have the coordinate system, the initial coordinate system, which is called ellipsoidal coordinates, is this correspondence here. It works on it really works on octants. Okay, it's not one-to-one. But anyway, here's the coordinate system. Okay, and then because you can see that you could solve if you knew all of the mu j's, you could solve going backwards. And it's fantastic. When mu is constant and you solve this equation, you get one of these quadrics, and it has its signature. We went through that last time. Okay, so by definition, this P is an antiderivative of this. Now notice it's only defined the way I've written it down up to a constant. But in here, we're only taking differences, okay? And what's really happening is that it's a contour integral where you're sticking to the upper half plane, okay? That's how you get from one to the other, and that's well defined because we're taking this simply connected piece of this. All right, so this is a coherent object, even though I haven't defined everything. Actually, now you can work out what I've said, exactly what everything is. Okay, so this is a very fancy gadget, but it's from the 1830s, fully understood maybe in the 1890s. It's pretty old, right? Okay, so of course, the next thing is to change to the U's here via P, and the insight that these folks had, especially Jacobi, is that the right way to consider integrals which are multi-valued, right? This thing unfortunately is multiple valued. The right way to do it is to look at the inverse function. The inverse function is way easier to understand, and that actually is the same thing that happens even with cosine and sine and with exponentials, even with the logarithm. The very first one of these functions is understood by the inverse, coherently, as opposed to not. So this is basically the beginning of calculus here, that people understood much better through special functions. And Riemann also spent his whole life doing contour integrals and stuff like this, and he's the one who did the theta functions, the Jacobi type functions in higher variables for the hyperelliptic integrals. So that's where Riemann surfaces were invented for this very purpose. Okay. So now, again, what's the goal? So let me remind you of the goal. The goal is that we want to cook up an algebraic expression which is going to produce for us the secret straight lines in this subject. The straight lines being the Bernoulli spiral type things, okay, in all dimensions, okay? And we're going to succeed halfway in all dimensions, and we're going to succeed essentially the whole way in dimension 2. Okay, so how do you do this? Well, the main tool is due to Levi-Civita. Okay? And remember I said that Abel invented abelian exactly for the group law, for this U1 plus U2 here, and in higher, this is exactly what he was doing. Levi-Civita understood much better what an affine connection is, okay, which was something that, people knew how to differentiate covariantly. That's the Christoffel symbols do that. But Levi-Civita had this brilliant idea of how you connect between an ambient space and a hypersurface. And that's exactly what we need here, is the connection between an ambient space and a hypersurface. Because the tool that we've got is this one scalar function, u, and the metric. So the only thing that's going on here is we have u and a metric. And of course we know that it satisfies the Laplace equation, which is, more generally, would be the Laplacian for that metric. So now the formulas I'm going to give you are valid for flat metrics. There are some extra terms which will clearly only use the curvature of that metric when you modify it. I have not worked those out, but you can tell that this is the case. And then there's also what you would have to insert in order to have a right-hand side. Okay. Now those are the types of things that Hamilton and Perelman and the like just did by hand afterwards. They always started with this kind of equation, and then you just put in the rest of it by hand because it's very routine. And you can see exactly when it's going to happen, which is when something depends on two derivatives of u. You have to put in something. So potentially you're going to have to put in more and more derivatives of whatever's on the right hand side. So that means that the eigenvalue equation, where it happens to be this guy, is going to be fantastic because only the first derivative, up to the first derivative, and then when you take more derivatives, it'll just be zero. So obviously the eigenfunctions are nicer from the point of view of this stuff. Okay, so let's get started. So the first thing is Levi-Civita. So what does Levi-Civita tell us? You take the covariant derivative, and it induces a covariant derivative on the tangent space. And the notations that I'm going to use are fairly standard here. So we're thinking of x and y being in a tangent space, okay, of some manifold. In our case, it's going to happen to be, the manifold will be m sub tau, which is u equals some level tau. Okay, that'll be our manifold. So what Levi-Civita says is if you take a metric, and in our case, it's going to be this very metric g here. This is g. Okay, so here's g. This is the standard thing that you do when you restrict to a surface. And we know what the surface is. The surface is u is equal to tau. All right? So this is a standard thing that you do. The covariant derivative, I'm going to have to know. When you have standard coordinates, I'm not going to. No. If you have standard coordinates, Euclidean coordinates, d by dx I, d by dx j, and you're in this with the standard metric. This thing is zero. And literally the only thing you have to know in this subject is the product rule. Okay? D by dxi, d by dxj. There has two terms. The derivative can fall in the A or it can fall according to this rule in the other one. Now, in general, these can be any functions here. Right? Any linear combination of them. Sorry. So it's not obvious when I write zero here that when I take the covariant derivative of a vector, I get a vector. So it has. So the general situation. Let me just. When you have a frame, the starting place of how you define a connection is you just prescribe these numbers, right? These functions, and so in our case, if we were in these coordinates, these numbers will be zero, right? And then the rest of it follows by the product rule. That is, when you differentiate a product, you do that. Anyway, I will never get anywhere if I explain to you all of differential geometry. So let's proceed. All right. So this is the induced connection. Induced connection. It only is defined for x and y tangent to the manifold, and this thing has a name. It's called the second fundamental form. Now, there's a symmetry property of the connection, which is written this way, and it's inherited by this connection here. And the way it's inherited for the normal component is it's that a of xy is equal to a of yx. So this is a quadratic form, and this process is the most unbelievably trivial process in linear algebra. It's literally, the requirement is that this be tangent. And the tangent plus the normal spans the space, and so therefore there's a unique way of doing this. And this was the insight that Levi-Civita had. And then the amazing thing is that this connection dg, the metric when restricted to the tangent space is covariant constant. So there's a way, once you've differentiated vectors, you can differentiate any tensor, and then this thing is constant with respect to this. So this is essentially the beginning of all differential geometry. Maybe, I don't know, it was Levi-Civita maybe the 1920s or something like that. Okay, so here's what we have to do. What we have to do is we have to replace the normal vector by an interesting other transverse vector. And it's going to be the right one, which is going to make the entire setup, all of the differentiations that we perform work. So let's do that. So here are the definitions. I'm going to organize them 1, 2, 3, where 1 means it depends on first derivatives of u, 2 means it depends on second derivatives, and 3 means it depends on third derivatives. All right? So the first object of study is the length squared. Okay? That we know because that's g of du. All right? So we know g and we know du, so this is an invariant way of saying that we got this guy. All right? So now, the next thing we're going to do is define the thing which sort of heuristically corresponds to d by du. And you can write it as grad u divided by the length of grad u squared. Okay? And so in quotation marks. All right? And I'll mention what it is invariantly too. Let's see. This one is if you take the vector field and it's a differentiation on a function, then this is by definition g of du df divided by g of du. Now this is what's always going to happen, which is that we get rational functions of du and g. That's all that's going on here. But they're just going to get steadily more complicated. All right, so the next thing I'm going to do, technically I don't need this, but it makes it easier for me to make the subsequent definitions. I'm going to introduce a frame, an orthogonal frame for the rest of the coordinates, okay? And you know, xn is just the w, and then there's a dual frame. I'm not positive I need this. Now, when you do that, the omega n is just du, all right? But the other ones are a little complicated because they have to be tangent to the right. They're orthogonal to w, and w is normal, so they're tangent. Okay, so that's it. So now here's the first interesting object. So here's 2.1. This I'm going to call beta. It's a symmetric two-form. To the real line, if we're in the real line, but in disguise, we could do the complex version. It doesn't matter for this. Everything's algebraic. So beta of xy by definition is equal to the W component of the connection. So the connection is yet another object which is algebraic. So it's a rational function of G, really G prime. You should say G and G prime. Okay, so implicitly I'm going to have to take different derivatives of G all over the line here, which of course is the whole point. The differential equations can be viewed as a differential equation of G. Okay. So what is this equal to? Well, this is just a multiple, right? W was just e to the minus alpha times the normal, right? That's all it was, right? Because that's divided by too many powers of the gradient here, all right? So this thing is equal to e to the minus alpha times a of xy, because what I did before, I noticed this was the normal component of this thing. And now I'm just multiplying that by a scale factor. All right, so I haven't done very much here. But it's very important to realize that individually, these two factors are not algebraic in what I'm doing. Okay? This one is, and these two, there's some cancellation between them, and this is a disaster for doing algebra. Okay, because there's a square root and the branches are a mess. Okay, so the next thing, but anyway, it's like the second fundamental form, etc. Okay, so now there's a distinguished vector v in the tangent space, and it's going to be defined as in duality with beta, with the form beta, right? So what it is it's the action of x on alpha. Okay, remember alpha was back here. It's the logarithm of this thing, and so now I have a tangent vector, which is dual to the operation. So it's essentially it's the raised index. It's v is beta ij. Xi, alpha, xj. This is another way of saying it, where beta ij is the inverse matrix of beta. Okay, but this is a slightly more canonical way of saying it. This is saying it in coordinates. All right, so this is the next object of study. It's a distinguished, interesting vector in the tangent space. And here's the first real crux, which gets us started, which is my new normal, okay? So what it is e to the 2 alpha times w minus p. So this is an ambient vector, and it's scaled in a specifically clever way. And remember, this is completely algebraic according to what I've done so far. And this is the guy which is going to replace the normal in our Levi-Civita style. Now, this is an exact imitation of what happens in affine geometry. That affine geometry has a beautiful history, and Calabi used it to characterize the entire solutions to the Mogent-Perry equation. It's a very jazzy thing, and it involves something called the affine normal. And I'm imitating that construction here, all right? So what's the next thing we're going to do? We're just going to imitate Levi-Civita, all right? So let's see if I can do this. So here's the what I would call the real starting place. Oh, I should mention one more thing. So here's the first place where you see that we've actually done the right thing a little bit with the geometry, which is that for the ellipsoids, nu is the radial vector. Okay, so we know we're heading in the right direction. But this very specific form has many more things which constrain it, as I'll explain in a second. So the next thing we do is we imitate Levi-Civita in the following way. We introduce a new connection, which is going to be tangent, and then a new quadratic form, which is almost the original second fundamental form, but times mu. Okay, this is easy to do because this is a transverse vector, and you just do the decomposition because it's a vector space. Okay, there's nothing going on here. This is a purely algebraic operation. Okay, and remember, this is just depending on the metric. There's nothing going on here. We're only using the metric. All right, so the next thing to observe is that if you take this covariant derivative, this new covariant derivative on the tangent space, and you act on the flux, which I defined in the previous lectures, you get 0. Okay, so this density, if you like, this was the thing which was the same as grad U times the area of the manifold. Okay, this thing is identically 0. Now, this is actually not very surprising, and this does not use the fact that Laplacian is equal to 0. This is just a level set phenomenon. It's not a big deal, and I'm pretty sure that this is known to people in affine geometry. So okay, so now we're going to step 3. So we're going to the third level. Now, fortunately, when we go to the third level, 50% of what we're going to do is mindless. All you do is you have the objects of study already, and you just differentiate them, and you see what happens. Okay? So the first thing that we're going to do is we're going to take what's called the cubic form, which is the derivative of L1. I didn't mention this, but this is another nice symmetric. This one, by the way, is called the first fundamental form because G doesn't exist in affine geometry. So there's analogous things where there's a different vector here in affine geometry. So here, y is. Okay, so this is the definition of this cubic form. So it's trivially, by definition, it's a tensor. But what's interesting about it is that it's S3 symmetric. In other words, you can permute all these vectors. So it's obvious that you can permute these because L1 was already symmetric in these two. But you can also trade it with X, which is totally unobvious. That in classical geometry, that's called the Cauchy minority equations, and it works here too. Okay, but that is one of the ones that requires that we have a flat metric. Okay, so that's this one, and now the next thing we're going to do is a little fancier, and this is called. I'm going to give this the name polarity. Okay, so it's a polarity 1 form. And it's going to be cooked up out of this one. And what it is for geometers, it's the contraction using L1 of this 3 tensor. And so by definition, that's if a 1 form acts on vectors, and the way you do it is you trace F with respect to a basis here, I equals 1 to n minus 1, but it has to be orthonormal with respect to L1. Oh, God, I just realized. Oh, yeah, that's right. That's right, with respect to L1. Okay? I forgot to mention to you that L1, what is it, in terms of beta? Did I write this down somewhere? I think it's e to the 2 alpha beta. It's just another multiple of beta. But both beta and L1 are algebraic, as you can see, because the 2 alphas are good. It's the single alphas that are good. All right, so here's the polarity. Now, in affine geometry, this tensor is identically 0. for all surfaces. I forgot to mention to you that for the quadrants, the cubic form is identically 0. And the polarity form is just identically 0. And that's worded, the word is called polarity, apolarity. So I learned this from a paper by Cheng and Yao, which is where I learned all this stuff from, the affine geometry stuff. And they said apolarity, so therefore I'm calling this polarity, because there must be some other people somewhere in the literature who did this some other way, but unfortunately this is the only place where I've seen it. That presentation is fantastic, except it's in the Cartan formalism, so that it's incomprehensible from this particular point of view. All right. So here's the third thing. So here's the next third order thing. It's called the shape operator, which is analogous to what you do in differential geometry. And it's sort of the rest of the derivatives. So S of x, by definition, is minus the covariant derivative in the ambient space of nu. Now, when you do this in classical geometry, it's not that it's useless, it's that it generates things that you already know about. It just, in disguise, gives you back the second fundamental form. So here's the miracle of this one. This is tangent. Okay? So this is very, very important, and this is really why this definition of nu happened, is so that this coincidence would occur. In other words, a priori this could have a transverse component, but it's actually always tangent. This, again, we're not using the fact that Laplacian of u is equal to 0. This is just true for all level sets. This is just a level set geometry so far. Okay? There was one exception, that radial statement that I made had to do with the harmonic property. Here we're just talking about level sets. Okay? So that means that S is a mapping from the tangent space to the tangent space. Okay? And the amazing thing about it is that in addition to this property, it has a symmetry property, namely that it's symmetric. L1 is symmetric with respect to, or S is symmetric with respect to the L1. Okay, so this is a standard property of the from classical geometry, but it turns out to persist here. And that means you can define a new tensor, which is a symmetric tensor, which I'm going to call L2, which again is a symmetric tensor on the tangent space. So in classical geometry, this is no new information, but here it's different. And this is the first place where you can really see that there's something going on here. Namely, if you take the coordinates, if you take u is equal to a constant times uj, any of the uj's, then the Lie derivative with respect to w of L2 is 0. And the volume element of L2 is the flux, is the thing that I had before. So this is hiding underneath. There's a much better law here, at least for the quadrants. And this is, and in fact, for the ellipsoids, it's this constant sphere. This guy, all right, and it's another standard thing for the other quadrants. Okay, so this is the next invariant. Now we're almost done with the invariants because we've graduated to the third degree here. Okay. So now we're going to do the next thing we're going to do is we're just going to put these things together using some linear algebra and some other simple stuff. Okay, so I'll leave these things on the board. And yes. So what's the next one? 3.5. So linear algebra. I'm going to combine this quadratic form with another term, which is the polarity times d alpha restricted to the tangent space. Totally legal for me to do this. D alpha, of course, alpha is a great thing. The differential of alpha is completely well defined. I can restrict it to them. Okay? So here's my new guy. Now, this one, these two, L2 and L3, are the same on the coordinate systems. This is the one that's supposed to incorporate the tilt so that I can get all the other directions. Right? The polarity is for me, is accounting for the tilt. Okay? So now I can tell you what the 2D formula is. Okay, so here's the 2D formula. For G tilde. So here it is. G tilde equals, oh, yeah. So first of all, I want to extend L3 to ambient by L3 of W comma anything is equal to 0. So it's in the tangent space, but I have to extend it, and of course I know what W is, so therefore this is a coherent. This is just saying that it's expressed in terms of omega 1 through omega n minus 1, but there's no omega n. No cross terms, nothing. Okay, so that's just a convention for me. It's the way I want to extend it, right? And now I can tell you the formula. Oh, I have to do the same thing. I'm also going to extend P by P of W is equal to 0. P was also only defined on the tangent space. Okay, so now I can do the formula. So G tilde in the 2D case only is L3 plus a cross term. This is the symmetric product of two one forms plus the du direction, which was missing. So that's this expression here. It's the second covariant derivative of alpha evaluated at WW plus twice the gradient, the covariant derivative of W with respect to W acting on alpha times du squared. Okay, so it has three pieces. It has a tangential part, it has a cross term, and it has a term parallel to du squared. Right? And this is the one that works. So G tilde is equal to du1 squared plus du2 squared, exactly when it's the model. Okay, so it accommodates the tilt. So unfortunately, it's this complicated. So now what happens in higher dimensions? Okay, so I know something serious about what happens in higher dimensions, and I'm going to tell you, and this is supposed to explain to you why it's a little complicated to figure out. So one of the biggest difficulties is that in this model case where you just have a component, P is 0 and F is 0. That is, the cubic form and the polarity are identically 0. So you can't tell how much to put in of those things. It's very hard to tell what's going on. All right, so here's the recipe. So this is the n-dimensional recipe. At least when u is equal to u a constant times just one of the components. All right. So the first thing you do is you define a new linear map from the tangent space to the tangent space. And what you do, well. And now the way it's defined is the following. It's rather simple. So it's like it's the diagonalization of L2 with respect to L2 or L3, because I'm going to call it L3. But it's the same as L2 in this coordinate case. So right, L2 equals L3 in this case. So there's a unique linear map symmetric with respect to L3, which reproduces the metric, assuming that L3 is non-degenerate. You can always do this. Okay, so that's a linear map, and now we're going to take the characteristic polynomial of this map, right? And that is a polynomial of degree n minus 1, because remember, we're just on the tangent space now. Okay, this is an n minus 1. Now I'm going to define b tilde is equal to this polynomial differentiated once and evaluated at the matrix B. Okay? So this is the correct thing to do. And now, what I'm claiming is that G tilde is equal to L3 of B tilde, G tilde restricted to the tangent space is equal to L3 of B tilde inverse xy, evaluated xy. That's the formula. So the linear algebra, so this is correct. This is literally what it is. And it gives exactly in the coordinate cases du. So this thing is equal to du 1 squared up to du n minus 1 squared if it happens to be un. Okay? And it gives the right thing in all cases. So this is it. This has to be it because it's the formula. But I don't know yet how to tilt it. And that was the thing that created the 44,000 terms. So I don't know that I can. I'll say a few more words here. I think I mentioned some applications last time, and I won't have time to say anything. There's lots to say about that. But instead, let me say something else. Yeah.
In dimension 2, can you tilt?
Pardon me?
In the two-dimensional case, can you do the tilting?
Yes, that's what this formula that I up here is. This is the one that accomplishes the tilt. This is everything.
That's everything.
Yeah, this is it. It's just that in higher dimensions I can't do the tilt. That is, I have a piece of the tilt, but I don't understand the tilt. Yes.
Is there a simple formula for the Gaussian curvature of G tilde? Because Gaussian curvature is 0 if and only if the metric is flat, so it's the kind of thing that you want.
Well, so
Two dimensions.
in 2 dimensions.
The Gaussian curvature of G tilde.
Yeah, I mean, so because I've already got it, I'm okay with it. I mean, I'm interested. One of the things that, for example, that I said in the applications last time is that the volume element of G tilde is very interesting. The curvature of G tilde is very interesting in general. That's exactly the next stage of all of this stuff. Is once you've found G tilde, you go all the way up to 7th derivatives of U. And you ask questions about. So it's actually a second order equation for the Gauss curvature, as you're calling it, which I would just call the scalar curvature in this case. It's just some trace of the Riemann curvature tensor, which of course only has one component in 2 dimensions. So but that's exactly where the conjectures from last time were addressing exactly those issues. So let me just say one thing. So tip of the iceberg here. So we already saw the tip of the iceberg, which was that this thing was equal to 0. This was this wonderful property observed by Calderón. I just want to mention to you that if you take n of alpha, remember alpha is the log of grad u, n of alpha is the mean curvature, okay? And there's a more beautiful formula at the next order. If you take the Laplacian of alpha, so this is a formula which was discovered by my student Steve Fromm in the 90s, maybe 94 or something, 93, 94. The Laplacian of this is minus twice the scalar curvature. Okay, so this is what I would call the tip of the iceberg. Another thing is, you look here's this quadratic form beta, which seems sort of trivially the same as the second fundamental form. But there's a theorem of Chang, Ma, and Yang from 2010, which says that that beta greater than or equal to a constant times the metric on a tangent space. Okay, it satisfies a maximum principle. So this, I believe, is just a trace of the appropriate Hamilton matrix maximum principle. And indeed, there's an easy way to write down what the guess is. It involves directional derivatives of alpha plus this quadratic form. It's sort of in the same spirit as Hamilton's. So all of these things feel like they should have corresponding, stronger statements which underlie them. This is what I mean by the tip of the iceberg. So anyway, I think I'm going to have to stop here. Thank you.
Any further questions? Can you check the conjectures in 2 dimensions?
So can I check the conjectures in 2 dimensions? The answer is that as soon as I get my colleague Jack Lee to check them in 2 dimensions, we will have some. So there are enough coincidences here that I'm confident that there's something there. But obviously, until they're checked in 2 dimensions, it's not complete. But this is it's very, very close to being. I mean, I think it's totally feasible to do that in short order.
Right.
Check them in 2 dimensions, and then depending on whether they're right or not. So what this would give, there actually was one theorem that I mentioned that might have a better version. So there were these theorems that I mentioned last time, which are known in 2D, but one of the theorems that so one of the things that Calderón and I did was we characterized all of the, if this is simply connected, in a ball, and Laplacian u is equal to delta of u. Okay, so this is the situation. Also, u is greater than or equal to 0. This is what's called a one-phase free boundary problem because there's no negative component. Okay, so this is a famous free boundary problem. So we characterize these solutions. And inside of this ball of radius 2, when you look inside the ball of radius 1, what you see is 2 catenaries, or you can just have a smooth thing. So the only way that the curvature tends to infinity is if it rigidifies to something that resembles 2 catenaries. And this is completely analogous to a theorem of Kolding and Minkowski about annuli in the ball. And there's an overlap which is very easy for both theorems, which is there's a relationship between these solutions and minimal surfaces, which is due to Trizet. So that's a fantastic thing. So what's not known, so the one hope is that, as I was mentioning last time, is that this would give a proof of this, a completely different proof of this. But the thing that I wanted to mention that actually, even in 2 dimensions, there might be something more to be able to say is that what if it's finitely connected? What can you say? And the conjecture in the entire case, so there are only 2 pictures. There's this beautiful, it's construction, it's Hausworth, Euler, and Paccard are the people who figured out this global solution, all right? Which is essentially the image of z plus cosine z, or z plus sine z. It's related to this map, so almost the same maps that I'm doing here, but of course there's this delta function, so it's a different problem. Anyway, so you look at this conformal map and you get some shape like this, which is simply connected, and it's 0 over here. So the conjecture is that it's really in disguise. There are only two of these. The other one is the one connected one where you have a zero face here and it's on the outside. And then you can't have two bubbles. You can't have a doubly connected thing. The only thing you can get, and this would be much harder, is there's one with a whole sequence of bubbles, an infinite line of bubbles, and that's exactly corresponds to the Shirk surface in minimal surface theory. There's a one-to-one correspondence between these things. So there's a direct relationship between the topology of embedded surfaces and embedded minimal surfaces in this two-dimensional problem. And I'm claiming that ruling out the fact that there can't be two holes in this case would be something I would hope for this as well, so even in two dimensions.
Well, thank you very much, David. It was great.